This is our presentation for Abstract Game Engine. My group members are Ryan, Valerie, Benjamin, and Kai Fong. For the introduction, I will cover the 5 key components, such as the movement system, collision detection, input processing, scene management, and entity management. So with the help of OOP concept and solid principles, this ensures modularity and reusability across various simulation environments and enable efficient game logic separation for scalability and maintainability. So for the overall design, the game master acts as a central controller which controls all the game logic. And for the audio manager, it manages background music and sound effects with volume and mute controls. For the collision manager, it handles collision detection and response between the entities, such as destroying the entity or playing a certain music. For the entity manager, it manages creation and updates and deletes the entities. For the I/O manager, it processes the keyboard, mouse, and controller inputs and handles all the rendering, which affects the entity movement. For the movement manager, it controls the entity movement, which ensures a smooth update per frame, such as moving up and down or left and right, or moving to a certain position. While for the scene manager, it manages the game scenes, transition, and active states. So, such as moving from menu scene to setting scene or to the game scene. And for the UI manager, it handles UI elements such as buttons and also text, which displays like menus or scoreboards. So this is what the game engine shows on start, with the menu scene that is managed by the scene manager. There are 2 button components managed by the UI manager. The settings button is mapped to the go to scene action to go to settings scenes with the help of input manager and scene manager. So when transitioning to new scenes, there's a transition effect which is also managed by the scene manager. So this shows the settings scene with 2 buttons and 1 slider UI component. The slider component is mapped to the change volume action, which adjusts the volume based on the slider value as such. So the mute button is mapped to the toggle mute action and will toggle between setting volume to 0 and 100, with which it interacts with the input manager and the audio manager. So next, I'll transition to the game scene. This shows the creation of entity with its respective colliders and the mapping of input for player movement and other AI entity movement. So the red rectangle entity uses the rotate towards and move to movement, which rotates and moves to a certain position. While the purple polygon is able to instantiate with any number of sides with its polymorphism for the constructor, and it also uses the move forward movement. And this also uses the collision detection to restrict its movement out of the scene. Whereas for the green circle, it actually moves from waypoint to waypoint to any position that you set with. And the yellow polygon uses the chase target movement to follow the entity. So next, I'll demonstrate the input for controlling the player character using WASD keys, which is also mapped using the input manager, and using the mouse drag to drag the entity away. This is using the keys, while this is dragging. So when you drag, the yellow polygon actually chases the player. So next, I will show the detection for collision between player and the purple polygon. So when it collides, it actually destroys the purple polygon.
Now I'll be talking more about the managers that we have implemented within our abstract engine. And each manager serves a specific purpose to organize and control the type of object that it is meant for, which you can see here in our entity manager image shown on the right. By storing a list of entities created, it allows us to control the entity's lifecycle and ensure that each entity is unique from one another. The entity manages draws and clears entities that are in the list for the application. Next, we have the collision manager, which helps call the creation of a collider by using a collider factory, and it then maps the collider to an entity. It is also responsible for detecting and registering the collision of 2 entities and process the events that will happen. Then we have the I/O manager, which processes the inputs by mapping each input to an action. It also handles the mouse inputs with their implementation on the tracking of the mouse action and the coordinates of the cursor. We have audio manager, which stores a mapping of each loaded music and sound effect with its respective audio file name. This allows the handling of the volume and playing of each audio object. The manager also keeps track of whether all sound is built up by using a Boolean stored in the manager class. The movement manager contains a list of each registered entity, and then allows the mapping of the list of movement types to an entity. It also processes and updates the movement of all registered entities. The scene manager stores each scene that is created in the application into a stack, and it disposes and renders the correct scene for the application. It also stores the type of transitions between scenes. And lastly, we have the UI manager, which stores the UI components in the list, sets, and clears the UI that are in the list as well. Now I pass my time to Kai Feng to explain more about the object-oriented principles used.
Thank you, Benjamin. Next, we'll be going over the object-oriented principles used in our system. Encapsulation restricts direct access to class intervals, improving security and preventing unintended modifications. For example, private variables can only be accessed through public methods. Inheritance allows subclasses to reuse functionalities from parent classes, while polymorphism methods like play behave differently across different subclasses. Abstraction simplifies complex logic. Methods like load assets hide internal details, making the code easier to manage. Our project also used two key design patterns. The singleton pattern ensures that only one instance of the class exists. This is used in all manager classes such as Audio Manager, Collision Manager, and Scene Manager for centralized control. Factory pattern is used in Collider Factory to create different collider types dynamically, improving flexibility and reusability. Our project is also guided by the solid principles. Firstly, for single responsibility principle, each class has only one reason to change. For example, Audio Manager handles only audio-related tasks to ensure modularity. Secondly, open-close principle ensures that our classes are open for extension, but closed for modifications. Entity can be extended with new types without changing its original code. Thirdly, Liskov substitution principle ensures subtypes must be substitutable for their base types. This is seen in game character and non-character, both extending entity and working interchangeably. For interface segregation principle, clients should not depend on unused interfaces. We achieve this by defining specific behaviors in the interfaces like iAudio, iCollider, and iTexture Renderer. Last but not least, for dependency inversion principle, high-level modules should not depend on low-level modules, but rely on abstractions. For example, Audio Manager depends on iAudio, which allows different implementations without modifying the manager class. Now, I'll be passing the time to Valerie, who will be sharing more about our UML diagram and engine limitations.
This UML diagram provides an overview of our abstract engines architecture. It visualizes how key components interact, including managers for audio, collision handling, entities, input processing, movement, scene transition, and UI management. Each module follows object-oriented programming principles to ensure modularity, reusability, and maintainability. The relationships between classes, dependencies, and data flows are structured to enhance scalability and maintain clear separation of concerns. This structured approach allows for efficient system expansion without major architectural changes. Next, limitation of the engine. While our engine is well structured, we identified several limitations. First, the Scene Manager and Audio Manager are tightly coupled, reducing modularity. To improve flexibility, we will introduce interfaces to decouple these components. Second, scalability challenges arises as adding new features may require significant refactoring. Third, performance bottleneck exists due to collision detection, which is resource intensive. Additionally, our movement system relies too much on inheritance, making it less flexible. We plan to adopt strategy patterns to improve adaptability. Lastly, UI complexity is a concern, and improvements are needed to streamline UI management and interaction. In summary, we developed an abstract engine using OOP and solid principles to ensure modularity, scalability, and maintainability. The core components include Game Master, managers for audio, collision, entity handling, input-output, movement, scene transition, and UI. By applying key OOP principles such as encapsulation, inheritance, polymorphism, and abstraction, we structured the engine for efficiency. However, we recognize areas for improvement, including reducing coupling, improving movement flexibility, and refining UI management. These refinements will be implemented in Part 2 through interfaces and strategy patterns to enhance performance and maintainability. This ensures that our engine remains adaptable and scalable for future enhancement. Thank you.